Hey guys, I just wanted to take a quick look at the solutions to your assignment from last week. So let's get into it. First one, we were told that in 5 seconds a hairdryer takes 10,000 joules of energy from the main supply. What is its power in watts and kilowatts? So pretty straightforward. Power is equal to energy divided by time. So we plug in our values and we get 2,000 watts, and that gives us the answer to part A. We then convert that to kilowatts by dividing by 1,000. And our conversion factor, of course, is 1,000 watts per kilowatt, which you can see right here. Okay, so that will give us a value of 2 kilowatts for the second part of your answer for part B. Okay, 2. An electric heater takes a current of 4 amps when connected to a 230 volt supply. What is its power? Well, power is equal to current times potential difference, or perhaps easier way to remember it, P is equal to IV. Okay, so we plug in current and we plug in our potential difference, 230 volts, and that will give us about 920 watts. If we want to be really picky about significant figures, then that would be equal to 900 watts to one significant figure. Okay, for number 3, we are asked to find the current for a light bulb of 36 watts connected to a 12 volt supply. So here we rearrange the previous equation and solve it for current. Current is equal to power divided by voltage or potential difference. Plug in our values and we get 3 amps for our answer. For number 4, both resistors receive the full battery potential difference because they are parallel. That is a characteristic of parallel circuits. So use the resistance equation in the box above right to calculate the current through each of the resistors. I did not do that. I just used Ohm's law to calculate the current. So here we can see that I have solved Ohm's law, the Ohm's law equation for current rather than resistance, which is its normal situation. So solve for current, plug in our values, and we get 4 amps through the first resistor and 2 amps through the second resistor. Okay, we would need the power for each of these resistors in order to use the resistance equation that they gave us there. So a little bit of a mistake there for 4A on the part of the textbook writers. For 4B, we're asked to calculate the power dissipated in each of the resistors. Here we do use the equation given. P is equal to I squared times R. Power is equal to current squared times resistance. Okay, so again, we plug in our values and we'll find that power through the first resistor is 48 watts. Power through the second resistor is 24 watts. There is a faster way to do this though, a way that does not involve calculating current first. So we have here the power equation, and we have over here Ohm's law. Okay, so we can plug the value for current into the power equation, potential difference divided by resistance, and that will give us this new equation where power is equal to voltage squared divided by resistance. So here's a way that we can calculate the power without actually calculating current first, so it's a little bit of a shortcut. And I'm going to use that shortcut again a little bit later. For part C, calculate the power of the battery. Well, if each component is drawing power, then the power put out by the battery has to be the total power of those components, okay? And this has to do with conservation of energy. That energy has to come from somewhere, and it's coming from the battery. So we don't actually have to do much here. Another approach would be to calculate the current through the battery, and you could do that too. So you would just add up both of these currents and then multiply it by the voltage. you should get the same answer, 72 watts. Okay. Next, we will look at if a battery of twice the potential difference was used, what would its power be? Well, we saw earlier that there are multiple ways to approach this question. So we saw earlier that power is equal to voltage squared divided by resistance. So here I have calculated the power of each. So this would be equal to P1. And over on the right, we would have P2. But this is the power with the new voltage, okay? And what you'll find here is that you get 288 watts. There's another approach where you could actually do this a little bit faster just by recognizing that we're going to see a proportional increase of the increase in voltage squared. And that's another approach that we use in IB physics quite a lot. I won't go through it here right this moment. But again, as is often the case in physics, there are lots of ways to approach problems. Okay, so that's our first problem set. Here's our second problem set, and really not too much to go through here. These are just definitions. Number 2, I skipped number 1 because it's only related to British power supplies, the British plug, and it's not actually that useful for people living in Japan or anywhere else that is not the UK. Okay, so moving on to number 2, what is a fuse and how does it work? So a fuse is a device. No, this is a device. Sorry. Here we go. A fuse is a device designed to prevent the overload of a circuit, which is dangerous due to the possibility of fire. So yeah, the main purpose of fuses is, well, there are actually 2. The first one is to stop fires, and that's kind of the most important use of a fuse. The second use of a fuse is to protect the electronics. So, for example, measuring devices called ammeters or multimeters will often have a fuse so that if you accidentally run too much current through your ammeter, you don't destroy the ammeter, okay? You're not too worried about fire in that situation so much as protecting your equipment. So those are the 2 uses of a fuse. So fuses work by breaking the circuit by melting when too much current flows through the circuit. So a fuse will be made of a metal that will melt at a certain temperature, and it has a certain resistance, and you can calculate those things, and then you can rate your fuse for when you want it to melt down. Okay, so number 3. Why should the switch always be in the live wire rather than the neutral? That's because the neutral wire in this particular example may or may not have a significant potential difference. And that's because in a grounded circuit, the earth wire can actually accept / provide electrons for the circuit. In other words, if you're grounding to the earth, then that is enough to complete a circuit. And this is kind of a weird thing to wrap your head around, but it is true. You only need one wire to transfer current if you have, or potential difference if you have a couple of earths. Okay, in other words, the earth itself can complete a circuit. Number 4, double shielded or insulated devices do not require an earth wire. So we live in Japan, and most Japanese devices and outlets do not have earthing because double shielding is required on all devices. Okay, number 5. Here I have solved our power equation for current. current is equal to power divided by voltage. We're asked to figure out which fuses we should use for these appliances. Okay. Basically, our fuse needs to be big enough that it can handle the power. So we want to go slightly up. So I used Excel, and I just threw this equation into Excel, and it's just a lot faster. I'm not going to go through the methodology now. I've showed you guys before, but if you use formulas in Excel, it saves a lot of time when you have to do multiple calculations. Okay, so once I know the current going through each of these, I can select the appropriate fuse. Okay, in most cases, I went above, except for the 1200 watt. What is that device? The 1200 watt iron. I gave it a 5 amp fuse, but you could, I suppose, rationally have gone up to 13 amps there, but it was close enough that I felt like that would be okay. Anyway, moving on to the last one. Calculate the energy supplied to a 60 watt bulb in 1 second, in 1 minute. Okay, so here we just look at our power equation and we rearrange it. So power is equal to energy divided by time, and this is one of those fundamental equations in physics. It just keeps popping out, keeps popping out, keeps popping out. So you really need to be familiar with it. So we rearrange it such that energy is equal to power times time. And once we do that, it's just a matter of conversion. So for part A, in 1 second, we find that 60 joules will be delivered to the 60 watt bulb. In 1 minute, we multiply that value by 60 for 60 seconds, and we get 3,600 joules. Number 2, a bulb takes a current of 3 amps from a 12 volt battery. What is the power of the bulb? Very simple, very straightforward equation. P is equal to current times potential difference. That gives us 36 watts. Okay, for part B, how much energy is supplied in 10 minutes? Here we take our previous answer and we multiply it by the time. And of course, we need to convert that time to seconds. So the conversion factor is 60 seconds per 1 minute. Does that, and we find that we have 21,600 watts. You could probably argue that this should be to one significant figure based on our previous values. So we could round this off to 20 kilowatts. To 1 sig fig. Okay, for part 3, a 2 kilowatt heater is switched on for 4 hours. Calculate the thermal energy given off by the heater in kilowatt hours and in joules. Okay, so this is one of those cases where we can use dimensional analysis to get a formula. So energy is equal to 1 kilowatt hours. So when we're talking about kilowatt hours, we're talking about a unit of energy. It's not a joule, but this is typically what you read at the meter at your house. Okay, so you have to pay for power, and the power guy or lady will come by your house and read the meter. At least that's the way it used to work. And that meter reads kilowatt hours, and it's a very large amount of energy, as you'll see later. And that makes sense because we use a lot of energy, and joules is actually a pretty small number for the amount of energy that we typically use. Okay, so this formula, or this unit here, is actually going to give us our formula. So energy is equal to 1 kilowatt hour, which is equal to kilowatts times hours. Pretty straightforward. So if we know that, then we can just take the values given in the problem, multiply them by each other, and we're going to have 8 kilowatt hours. Okay, so little dimensional analysis. Okay, we need then to convert this value to joules in order for it to be useful. Well, not necessarily useful in order to just solve the second part of our problem. So here is my conversion, and I have here first the conversion from kilowatts to watts, okay? And then the conversion factor for watts to joules per second. Remember that 1 watt is equal to 1 joule per second. And this is another one of those things that is so fundamental that you just instinctively should be thinking about joules per second when you see the unit watt. Okay, insert bad joke here, by the way. All right, so my final conversion factor is for time. There are 3,600 seconds in 1 hour. 60 seconds times 60 minutes gives 3,600 seconds. And we find that we have 3.6 times 10 to the 6 joules in 1 kilowatt hour. Okay, so that is a pretty big number, you will note. Okay, so then we do another conversion, and this is our final conversion. We take our previously calculated energy in kilowatt hours, 8 kilowatt hours, and we convert that to joules using the conversion factor that we previously calculated. So there it is, 3.6 times 10 to the 6 joules per kilowatt hour, and that will give us a total of 3 times 10 to the 7 joules down to one significant figure. Okay, for number 4, it's not clear if you didn't read carefully, but 1 unit is defined as 1 kilowatt hour. So when we're talking about units, we're talking about kilowatt hours. As I said, the electric company measures your energy usage in kilowatt hours. So this is all pretty rational. So first, energy is equal to 3 kilowatts times 5 hours or 15 kilowatt hours. So the cost is equal to the price per unit times the number of units. We're given the price per unit as 10 CU per unit. I think that's pence. I'm not sure. It's a British unit of money, and I have not spent a lot of time in England. In fact, 0. So sorry. All right. So that means that our cost at 10, we'll just say pence, 10 pence per unit times 15 units gives 150 pence. Okay, energy is equal to, again, 60 watts times 12 hours, and that will give us 720 watt hours. However, that is not the unit we need, so we have to convert that to kilowatt hours, and we do that just by dividing by 1,000. I've kind of hustled things along here rather than show the conversion factor, but hopefully you can follow along. All right, if we have 0.72 kilowatt hours, we multiply that then by our rate, 10 pence per unit, and we get 7.2 pence. Okay, finally, for number 4, 1,200 watt hair dryers run for 15 minutes. So 1,200 watts is 1.2 kilowatts. I've skipped the conversion here. Again, hopefully you can follow along. And I'm then converting my minutes to hours to get kilowatt hours. So my conversion factor is 1 hour is equal to 60 minutes. And that will give me 0.3 kilowatt hours. There are a lot of ways you could have approached this particular conversion here. Once I have that, then I multiply it by 10 for my cost, and I will get 3 pence. So there's running a hairdryer. All right, for the last one, the power savings is going to equal the power of the 60 watt light bulb minus the power of the 15 watt light bulb. Okay, so first we need to calculate the powers of the 60 watt bulb and the 15 watt bulb. And we'll find that our 60 watt bulb, when multiplied by 6, uses 360 watts, and our 15 watt bulb uses 90 watts. So the power savings is 270 watts. Okay, to get the energy savings, we multiply that times the amount of time we use the bulbs on average, which is 4 hours. So we save 270 watts, multiply that times 4 hours a day, and then multiply that by 365 days, and we get 3.9 times 10 to the 5 kilowatt hours. Maybe. I might have to double check that. That may be watt hours. I'm going to have to check that. Anyway, this will give us 3.9 times 10 to the 6 pence. And yeah, let me double check this number. I may have skipped a conversion factor. This is what happens when you do physics problems too late at night. Okay, guys. Yeah. Caveat on this last solution, but I think the rest are cool. Let me know if you spot any problems, and I'll look forward to seeing you soon. Have a great day.